Hello and welcome back. We now discuss in a bit more detail how we can evaluate regression tasks with machine learning. What we want to do in regression is to predict a number. In most regression tasks, just predict a single number. Let's say this is sort of a naive approach, and we assume, at least implicitly this is done, that this single number is the mean. We've also encountered previously the quantile regression where we predict a specific choice of a quantile. But as you can see, we really need to understand the probability distribution, and if this has a high variance and long tails, this is not easy. So we can start by defining our prediction error. This is the difference between the true value y, the label or the target, and the predicted value y hat. And this is what you mainly see in many regression tasks. So assume that our machine learning model is perfect. We don't have anything to worry about that at this moment, so it's just an assumption. And let's stick with the naive model interpretation that the single number we get out from such a model is the mean. The true value, however, is a random variable following this probability distribution. And as you can see, if we have a large variance or long tails, we cannot expect those two values, y and y hat, to coincide, at least in principle even. This gets worse and worse if we have higher variance or longer tails. Even if the machine learning model is perfect, we cannot assume that this prediction error defined by the difference between those two single numbers is getting close to zero. We can even make this slightly worse. We still assume our model is now perfect, but we don't have to predict the mean, right? We can predict any quantile with our machine learning model. So let's say we predict a very high quantile, the 95% quantile. So this is far out in the tails. The true value is again the random variable following the probability distribution. But now the difference between the two of them will be even larger. But neither of the choice is wrong for our prediction. It just depends on the application, if we want a low quantile or a high quantile. So we need to really discuss evaluation metrics. Two of the most popular ones are the mean squared error and the mean absolute deviation. And we go back to comparing these single numbers. And this is what's mostly done in practice. And it's a starting point, but as you have just seen, it's not the end of the story. So the mean squared error is the squared difference between the single numbers of the random variable y and the prediction y hat. It's a quadratic metric. That means that there's a strong emphasis on points where y is far away from y hat. That does sound useful if we think about it naively. But if we have a distribution with high variance, we will have a lot of points where the difference between the prediction and the true value is very large. There's a variance of this, there's a root mean squared error, it's simply taking the root of it. Another popular measure is the mean absolute deviation. Instead of the squared difference, we take the absolute value of the difference, so this is a linear metric. It does have the benefit that it's more robust towards those outliers, and it's a good default choice when we want to evaluate single numbers. This is because it's not quadratic, so it doesn't penalize or put such a strong emphasis on points where this difference is very large. Let's compare the two for a simple toy example. Let's say that our prediction is the true value with some Gaussian random noise. So this is not really a big model, it just means that everything is perfect. We just assume that our prediction takes the true value and adds a little bit of noise to it. So essentially we say that the prediction, so to say, is the true value on the diagonal line here, but a bit smeared out due to the noise. This is as good as it possibly can get, and will never be as good in real life. Now we compare the behavior between those two metrics. Let's say we have 500 events in our test sample, and we compute on those 500 events the value of the mean squared error and the mean absolute deviation, and then we normalize to this one, so that at the end we always have a value of 1, right? Now we order the two metrics by the deviation, by the square the mean squared error by the squared difference, and by the MAD by the absolute value. And now we visualize how many events contribute to the metric. For example, at 80% of the metric, remember we normalize to a value of 1, so we look at the horizontal line at 0.8 on the y-axis, less than half of the values contribute for the mean squared error, because we've already contributed so much from all the other events. However, there's nothing to it, because we have the best perfect model that we can possibly have, which is just a bit of noise to it. So that means, because the mean squared error puts such an emphasis on those values that are further apart, we don't actually evaluate our whole test sample, and this is quite dangerous. There are other metrics. They are relative metrics. They are the MAP and the MASE. The MAP is often called mean absolute percentage error, and as you can see, it normalizes the absolute difference by the true value. Now this has its own issues. On one hand, it's good because we get a relative metric and not an absolute one, so it's a bit easier to follow and understand what's going on, but it requires that the true value is always greater than 0, otherwise it's not defined. So this doesn't necessarily happen all the time, especially if you have rare events or small events, and it also can introduce a large bias for small values. Another one is the MASE, the mean absolute scale error. This takes the MAD and compares this to a naive model. Now we introduce a sort of naive prediction that can be good or bad, but it can lead to a bias depending on how this naive model behaves, because inevitably we wouldn't call it a naive model if it were performing very well in all cases. So what can we do? So there are different measures we can take, and we really need to look at more than one single metric. One thing we can do is a diagonal plot. So we go back to the case we just had and say the prediction is always a good estimate of our true value, otherwise we wouldn't build this model. And this is true for all values, right? Remember our best case where we just added a little noise. So we imply here that if the model is good, all the pairs of y hat and y should be on the diagonal, or they deviate from the diagonal depending on the noise that is present. We cannot live without the noise, we have to accept it, but if we have an unbiased prediction, it would be sort of a point cloud around the diagonal, so that should be okay. And if we observe any systematic deviation from this diagonal line, we have a bias somewhere, and this is not okay. So this diagonal plot, as it's called, allows us to identify regions where the model doesn't perform well. Let's have a look at this example. You can use it as a scatter plot as we've done previously, but obviously we can't really see what's going on. On the x-axis we put the prediction, on the y-axis we put the true value. If we have a lot of data points, we can't really determine how things are going. So what we do instead is we split the x-axis, that this is the prediction, into n bins, and for each bin we calculate the mean of all values that fall within that bin. Then we also need to calculate a dispersion parameter. We are free in our choice here, some are better than others. We could use the standard deviation, the variance, the root mean square. The choice actually depends on the use case. And all points then should be statistically compatible with the diagonal. So we can see here in this example, in the region between 15 and 30 or so, the model is quite good, but it starts to show a bias towards low and high values. In this simple example that we had before, our prediction as the true value plus noise. That we said was a perfect prediction, but why do we then see these problematic areas towards small and large values? Well, it's simply to do with the edges. We have very small error bars here, so we have very few events, and that the calculation is very unreliable that we need for the dispersion parameter. But we also added the noise, right? So that means that the y-hat distribution is always wider than y. That means that all the y values, the true values, get shifted outwards because of that noise, but never back. And that introduces the bias we observe in the diagonal plot. So as you can see, it's quite sensitive as an analysis tool. So evaluating regressions, to recap, is really full of pitfalls. Most metrics you will encounter are metrics for single numbers, such as the MSE, MAD, MAP, and so on. They don't consider the variance, and you have also biases in various different ways, and each of those metrics has a bias in slightly different ways. What we can do, for example, is look at residuals and their diagonal plot to help identify regions with bad predictions. This also relies on single numbers. We also have much more advanced methods, which I just mentioned here, like probability integral transforms or inverse quantile profile plots, which we won't discuss here in detail. But you should be aware that this is not the end of the story.